All right, so today we are going to start our first topic. Uh, and my plan is to go as far as possible in chapter 2. And probably we'll still need 1 more hour next week to talk about the Bayes rule and maybe solve more examples on conditional probability. But the main topic for today's lecture will be to introduce you to certain terminology, sample space, outcome, event, things like that, and give a foundation of how we compute probabilities. Um, all right, so going over the axioms of probability. So that's the idea for today. So if I let me download the lecture slides from my scheduled web page, week 1. And sometimes the way I'm going to conduct this lecture is sometimes I'm going to refer to the book. We are going to look at the examples in the book. And sometimes I'm going to go over the slides, so back and forth. And sometimes I'm going to use the whiteboard. All right. And as usual, if you have any questions, feel free to interrupt me anytime by speaking up or writing in the chat box. I will try to regularly monitor the chat box for your questions. All right, so we went over the syllabus related material last time, but also if you have any questions about the course conduct before we start, also feel free to ask your questions about course conduct. Your first quiz is not going to be this week, not today, but 1 week from now. On Thursday next week, you will have a short quiz, probably just one question. This is what we plan on chapter 2, on what we will see in the following 3 hours. Okay, 2 hours today and 1 hour on Tuesday. My plan is to finish chapter 2. All right, this is our textbook. Yeah. Now, so the first part of this class is about probability, random variables, distributions of these random variables, the probability density function, probability mass function, cumulative distributions, and we are going to talk about these. Now, probability is the study of uncertainty, and it's every day in our lives. There are sometimes nice puzzles related or questions related to probability. Sometimes it's really unintuitive. Probability is not always intuitive, especially, for example, I remember when I play some cards with my dad. For example, what he has observed up to now, he thinks it will affect what it will come next, but sometimes it really shouldn't affect. For example, if I got the first 3 aces in the remaining deck of cards, whether the remaining ace is going to come to me or to him shouldn't matter whether I got the first 3 aces, okay? Given that knowledge, it shouldn't change the probability, but intuitively, human mind doesn't work like that because he may think, okay, the probability that four of the aces goes to you, all of them go to you, is really low probability. The remaining one should get to me. So, but that's not mathematically true, but sometimes probability is really very counterintuitive, and there may be interesting tricks about this. And another puzzle you may know, and we may talk about this example when we talk about conditional probability, is this. Was it a quiz show? I'm going to remember the name. It's about the doors, and there's a prize behind one of the doors, and 2 of the doors do not contain any prizes. So you choose a door. Yeah, Monty Hall. Exactly. Thanks, Sparta. Yeah, the Monty Hall problem. That's also a puzzle. Even famous probability theoreticians or researchers may fail to get the correct answer in that Monty Hall problem. Yeah, there are three doors. One door contains the prize. You select one of the doors, and the host opens it, and there's nothing behind it. The whatever you have chosen. Do you change your initial choice, or not, it's actually the host does not open the door that you have selected. The quiz host opens the other door that you haven't selected, with no prize behind it. Okay, so do you change your initial choice or not? So this was one of the problems. So we are going to talk about that later, but most of the time, people think that, I mean, it shouldn't change. It was your initial choice was not based on anything. You had 33% of chance, right? I mean, should you, and now there are two remaining doors, should you change it or not? Because I mean, most of the people are going to stick to their original choice, because also there is the counterintuitive way of thinking that the quiz show host is, I mean, not the quiz show, the Monty Hall host is actually trying to trick us to change our decision, so we get defensive against changing our decision. But we'll see that in this problem, changing your initial choice of the doors actually is a wiser idea, which will increase the probability of finding the prize. But again, this assumes that the host doesn't do anything deliberately to make this change. So yeah, that's another. Assuming that everything is independent, changing the choice makes sense. So things like that. So probability is every day in our lives, and as I gave this example not to talk about the conditional probabilities and stuff. We are going to come to that later. The reason I gave this example was to show that probability is sometimes very counterintuitive, and most of the time when in our daily lives, if we make decisions not taking the probability into account, but if we know probability in a better way, for example, if you're playing backgammon, if you count the probabilities and know your probabilities, it may help to win or to get better results. Okay, but at the end, there is uncertainty. Whatever you're doing, you may choose the more likely choice to give you success, but in probability, there is nothing certain. Okay, certain things that, I mean, the entire sample space, maybe there may be probability of one, maybe certainty, may indicate certainty, but in most of the problems that we are going to study, the probability is going to be somewhere between 0 and 1. It means there's uncertainty. We cannot be 100% sure. And in this class, we're going to label all such uncertain events as a random experiment. That random experiment may be tossing a coin, tossing a coin 5 times, observing the lifetime of a light bulb. For example, you have a light bulb, you observe its lifetime, how many days it's going to last. And that's a random experiment. Okay, so all these random experiments are random phenomena, random observations that we're going to have. So tossing a coin, the outcome is either heads or tails if you're tossing a single coin. So the outcome sometimes may be discrete, as in the case of tossing a coin. It's one of the two things. And observing the lifetime of a light bulb, again, it's a random event, but the outcome, if you're measuring it in milliseconds, for example, it may be, I mean, there's always this philosophical thing between discrete and continuous things. I mean, if you can always, if you, even if it's continuous, I mean, what I was going to say was, this observation, the lifetime of a light bulb, actually is something, the random variable that we're observing here is continuous random variable. It can be, for example, 12.1 days or 15.62 days. But you may always argue that whatever your precision is, there are finite number of things that you will be measuring. Why is it not called also discrete? So distinction between discrete and continuous is sometimes we just take that leap and say, I mean, at the quantum level, for example, we have the quanta, the packets, even the nature is not continuous, right? I mean, physicians have shown that as you get smaller and smaller, you cannot break particles into smaller than things, what we know as the quantum particles. So it's even nature is discrete in that sense. But we don't, when we're measuring things, when we're measuring the intensity, the radiance of light, for example, when you're using the real number, it's not in the mathematical sense. The real line is not cannot be infinitely divided in real life, but we're going to assume that when we're measuring something like the lifetime of a light bulb, we are in the real line. But what I mean is that the numbers that we're getting at the end are real numbers, like 12.2, 15.62, and these are continuous random variables. For example, if you were a fan of the Cleveland Cavaliers, if you're following the NBA, for example, the number of games a certain NBA team is going to win this season is also a discrete random variable. It's because it's an integer. All right, so integers are discrete. Things that have finite outcomes like heads or tails, or throwing up a dice, again 1 to 6, 1, 2, 3, 4, 5, 6, a single die or a pair of dice. The outcomes are discrete at sometimes, and sometimes they are real valued. And these are random experiments. So a single random experiments, first we should define as the experiment. And the way after the experiment is defined, this terminology is very important. An outcome, okay? A particular single observation of an experiment is called an outcome, okay? Sometimes when you're first reading this chapter, these two terms, outcomes and events, you may confuse them, okay? Event and an outcome are two different things. So event and outcome, these are the first two important terms that I want you to make sure the distinction between them to be able to read the chapter and understand what is going on there better. So event and outcome are two different things, okay? So when we perform an experiment, a particular specific observation of an experiment is called an outcome. Now, let me, some of these terms are maybe abstract, so I'm going to try to explain them best with an example. So let's assume we toss the coin 5 times. That's the experiment. Tossing the coin 5 times. Okay, so this one will be, for example, head, tail, head, head, tail, tail. Okay, so this is the first coin toss, second coin toss, third, fourth, and fifth. I toss the coin 5 times and I record what comes each time I toss the coin, and this is the whole entire experiment. An experiment is tossing the coin 5 times. That's a random experiment. And this here, what you see here, this line, is a specific outcome. All right? The set of all possible outcomes, it's called the sample space. That's another term that we are going to use, sample space. Okay, the set of all possible outcomes. And in this case, for example, the set of all possible outcomes is going to contain many things. Okay, a certain each of these outcomes. So here, how many different, we can ask different things. So I haven't defined what an event is yet, but the number of different outcomes you can have here is 2 to the 5, right? Each time the first coin toss can be head or tail. The second coin toss could be head or tail. So I can write 2 to the 5 makes 32, right? I can write 32 different outcomes here, okay? Now, here is what I'm going to define. An event. So the sample, in other words, the sample space is going to contain all the possible outcomes. So the size of the sample space here is 32. So if we are going to use the set theory analogy to describe most of the concepts here in this in this chapter, in the introductory chapter. If the entire set of outcomes, okay, one observation is head, tail, tail. One observation may be all heads, heads. Another observation, tail. So these are all individual outcomes, and there are 32 of them. An event, now I'm describing event, an event is a subset of the sample space. Okay, so this may be an event. This outcome, just a single a set which contains the single outcome may also be an event. But let me describe a different event, which is you toss the coin 5 times, you get at least 3 tails. Okay? Now, this sentence that I described contains this outcome, but it contains many other outcomes as well. Okay? Let me just repeat the event that I just described. The event that you toss the coin 5 times and you have 3 or more tails. Okay? As you can see, this one contains this TTTTT, HT. Okay, so this one is also in the set. All the subset of outcomes in which I have 3 or more tails in it will constitute the subset, and that's what we call an event. Okay, so if there are so how many different events are there? How many different events I can describe? So any ideas? For example, if for this experiment, for different experiments, you can have different events. So all the possible subsets that I can have with these 32 outcomes, right? It's 2 to the 32. So this is the power set of this. I can define 2 to the 32 different events for this experiment. And 2 of these events are very special, which is the empty set. So the 2 to the 32 contains the empty set as the subset. Okay, so the empty set is the subset, and the set that contains all of the events are also subsets. And these are described as simply no result subset, no results. So which is this empty set saying that you toss the coin 5 times and nothing happens. Okay, so that doesn't make sense, right? That's an empty event with a probability of 0. We are going to associate this empty set will be associated with the probability 0. And at the other extreme, the event that contain all of the outcomes here, which is a set of 32 outcomes, the event that contains all of the outcomes in it, that's that subset, can be translated into English as the event that some result will happen. You toss the coin 5 times, you'll get 5 something. Okay, so as you describe the event like that, it's not very meaningful. Of course, you're going to get some result. So here's the thing: when I say "of course you're going to get some result," that of course says that we associate the probability of 1 to this some result event. So we usually do not have these no result or some result events, which are indicated by the empty set and the set that contains all of the outcomes. The set of all of the outcomes is sometimes also denoted by this special omega symbol, which indicates the sample space. Okay, so the sample space here is sometimes indicated by this omega. Okay, so that contains all of the outcomes. So let me actually go ahead and make sure that I describe. I use the same notation. Yeah. So omega is our sample space, and the empty set is the empty event, and we can associate a probability to an event. And an event here, I repeat, an event is not a specific outcome. An event describes a subset of the sample space, a set of outcomes. Okay. For example, what kind of different events you can define with these heads and tails? For example, one event may be the first two coin tosses are heads, head, head, and then I don't care about the rest. So it may be head, 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 or head, head, tail, head, 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 tail, head, tail. So all the 8 outcomes in which the first two are heads will be a subset. It will contain 8 outcomes out of these 32 possible outcomes in this experiment. Okay, so this distinction is very important for you to understand what's written in that first chapter, because sometimes,
Hocam,
yes.
could you repeat the part that you described defined events?
Yeah, yeah, of course, because that's really important. Sometimes, because the term event is easily mistakable to a single event. All right, when we talk about a single outcome, an event is not the result of a single experiment. An event is, when I give an example, an event is something, for example, you describe like you get at least 3 tails. That's an event. Okay? When you say you get at least 3 tails, that English sentence defines a subset that of the sample space. So an event, mathematically, it's a subset of the sample space. And the sample space contains all the possible individual observations, which are called outcomes. An outcome, when you perform a single experiment is the tossing of 5 coins. Okay, so in different cases there may be, I mean, this in this example I set up my experiment, random experiment, as 5 coin tosses. Okay, now we could have from our lecture slides, let's also, to increase the number of examples we can have, look at this experiment, observing the lifetime of a light bulb. Okay, here the sample space actually is infinite. The sample space, for example, observing the lifetime of a light bulb. What's a specific outcome here? A single outcome can be 12.1 or 15.11. Okay? A single observation, when you observe the lifetime of a light bulb, a single specific observation is called the outcome of that experiment. And the set of all possible outcomes is called the sample space. So, sample space, outcome. Here, the sample space is infinite. When we have a continuous random variable like this, you can have infinitely many different outcomes. So the sample space in that regard is not, it's infinite, but it's not unbounded. For example, uh, can you have a light bulb with lifetime -2? No, of course not. It's probably, I mean, it starts at 0, goes all the way to infinity. We don't know how long it's going to last, how long it's going to end. All right. So, but still, the outcomes we can observe are infinitely many. So the sample space is infinite. Now here is an event, example of an event in this case, a subset of the sample space. What can it be, this subset? For example, let me define an event. The event that the lifetime of a light bulb is at least 10 days. Okay? This is an event that I described. The lifetime of a light bulb is at least 10 days. I define an interval on the real line from 10 to infinity. In that case, the subset itself is also infinite, but it doesn't matter. It's still a subset of the sample space. So any subset of the sample space is an event. That's what an event is. The 32, the number of outcomes, this 32, we got it from the nature of the experiment. Each time I toss the coin, there are two possible outcomes of a single coin toss, right? Head or tail, head or tail. This can also be head or tail. This can also be head or tail, head or tail, head or tail. So if the number of possible outcomes here is 2 to the power 5, it's if I didn't multiply this incorrectly, 4, yes, 16 multiplied by 2, 32. Okay, so it's here the size of the sample space is 32, but in the other example, the size of the sample space is just the size of the sample space was infinite. For example, let's what is the sample space? Let me get a new slide here. Let's talk about which is the same example in the book. The result of a single football game. So two teams play football, and there are three possible outcomes, right? Whenever a football game is played, if you're just interested in the final score, for example, team A is playing with team B, there are three possible outcomes. A wins, B wins, or it's a draw. Okay, so here these are the outcomes. So all of these together, the three of them. Now in this case, the size of the sample space is 3. Okay, it's not, we don't get, oh, it's A wins, B wins, draw. It's not. So this the sample space itself that corresponds to the 32 we have found in the previous example. Here it's just 3. The size of the sample space is 3. But the events here, again, an event is a subset of this sample space. What kind of different events you can define? For example, an event is, and the number of events you could have is going to be 8. You're right. You can define 8 different events here. Okay, and 2 of them are going to be nonsense events, which is meaning that nothing happens after the game. Neither one wins or it's not a draw. No result happens. No, after a football game, a result should happen. Maybe, I mean, if you consider the referee canceling the game, calling it a no result, it may. But then in that case, it should be listed in one of the outcomes. Okay, we just consider football games which end gracefully, and for football games that end gracefully, are outcome space. Whatever we can observe, this sample space contains everything that we can observe as individual outcomes. Okay, so that's our outcome list, which is called the sample space. And an event is a subset of this, any subset. Okay, for example, this one. This is a subset. Or this one, A wins and B wins. Okay, so look at this event. This event does not mean that both of them happens at the same time, right? This is something else. We're going to come to that. This cannot happen actually. A wins and B wins are two different things. Either, I mean, they cannot happen at the same time. But what does? Also, and if there is at least 3 goals, that's if you now count the number of goals, you define a different experiment. For example, the number of goals scored in a football game. In that case, we will have the sample space again may be infinite. Okay, because if there are no upper limit to the goals that you can score, but it may not be infinite. For example, if you can say that you can score at most 1 goal every 10 seconds, then it will not be unbounded. But if you look at this, what is this event? A wins or B wins. I can define this event in English as the game does not end with a draw. Okay, look at this event. The game does not end with a draw. Or an alternative English sentence that describes the same event E is either of the team wins. one of the teams is going to win. Okay, that's an event. One of the teams is going to one of the teams wins. One of the teams wins is an example event. So this event. Neither of the teams win. Okay, neither of the teams win. It's this event. Okay, so and or another event. The team A gets at least 1 point. If a win is 3 points and a draw is 1 point, the event that says team A is going to get at least 1 point. Okay, so that event is going to contain A wins and a draw. Okay, so there's all possible subsets you can think of, and if the sample space contains these three outcomes, the possible subsets you could have is going to be 8, as I said, containing two of those nonsense, not nonsense, but I mean not practically used events. The empty set, nothing happens, or some result is going to happen that contains all of them. Yeah, A-B draw is also an event. A-B draw that contains all three elements. It says that the game is going to end with some result. Okay, and and we are going to associate now probabilities to these things. The entire sample space, the probability we are going to assign. So we are first going to, before talking about the axioms of probability, we are going to define probability to be something that is assigned to these sets. For example, and in that case, when we are using probability that is assigned to a set, we are going to use these curly braces. But after we go over the axioms of probability, we will go back to using we will assign probabilities to events, and in that case we are going to use the normal parentheses like this. Okay, so right now the only thing that I told you was probability of the empty set, no event, is 0. The probability of this is 0. I can write it like this: probability of this empty event is equal to 0, and the probability of the sample space, the entire sample space, is 1. Observing at least one outcome is that's what the sample space is. Okay, so an event, again, you should just pin it in your head. It's a subset of outcomes. It's not a single outcome. You can also have a subset of it, but in general, an event may contain multiple outcomes. And just remember this thing. For example, the lifetime of a light bulb. What is the event? Maybe the lifetime of a light bulb is between 10 and 15 days. Okay, that will be an event. The sample space definitely depends on the type of experiment. That those nonsense events, no empty set. So when you define the sample space, its subsets, the empty set and the entire sample space, the entire sample space are going to be two of those subsets, and we will consider them as subsets. But when we talk about outcomes, for example, especially in section 2.3, we will talk about equally likely outcomes. For example, if you have, and this will come after we define what probability is. For example, if we have some discrete outcomes and each outcome is equally likely, and what we will do is we are going to assign, in that case, this empty, the empty set is an event. But when you consider outcomes, there are 3 of them. Okay, if they are equally likely. So here, if you look at the set of outcomes, in the set of outcomes there is no empty set, there is no sample space. So again, you shouldn't confuse the event definition with outcomes. This empty set here, when you say when the nonsense event into sample space, again, you're confusing event with an outcome. An outcome cannot be an empty set. Okay, an outcome here. Here you should ask this question: can we have nonsense outcome in the sample space? The members of the sample space are outcomes, not events. All right? An event is a subset of the sample space. Okay, so what the sample space as objects, it contains outcomes. For example, here when I talk about the 5 heads in this slide, look at the sample space. In the sample space, I'm not going to have the empty thing. This is not an outcome. This is an event. So the outcome will not be a member of the sample space, but the event is a subset of the sample space. And one of these subsets is the empty set. All right. So this is, again, the distinction between event and outcome is, I think, extremely critical to. I mean, it's very simple if you get it the first time. Maybe I mean, if you got it, it may you may be bored a little bit here, saying that, oh, why are we? This should be very simple. Why are we still talking about this? But believe me, it may sometimes you may confuse this. I mean, if you're confusing it, again, it's also something natural because of the. Uh, I mean, even if English is your first language, events sometimes we use in English event to describe a single event most of the time. But here, event describes a set of outcomes. An event is like the lifetime of a light bulb between 10 and 15 days. That's an event. Therefore, an event describes a set of outcomes in it. Okay, like the event.
Hocam,
Yes.
I understood all properties of an event, but I couldn't understand the empty sets part.
Yeah, the empty set is the sample space has different subsets, right? An empty set is one of those subsets. So the empty set is an event which is associated with the probability of 0. So in reality, I mean, in practice, we don't observe that event. That's you can consider the empty set, which is a subset of the sample space. Okay, so the sample space is this. There are 2 to the 32 subsets. 2 of these 2 to the 32 subsets, one of them is the empty set, and one of them is the set that contains all the outcomes in it. Okay, all 32 outcomes in it. That's also a subset of the sample space. The empty set you may think about in English as if no event or nothing happens. Therefore, that's why we associate a probability of 0 with it. It doesn't happen, all right? We can be certain that empty set is not going to be observed as an outcome. So just consider it as one of the extremities that says nothing happens. Okay, and nothing happens is not one of the outcomes. Not we will when we perform an experiment, one of these specific outcomes will be there. So the empty set event, it defines like no outcome, and it's not possible. That's why when I say maybe that's what makes it difficult to understand the empty set, because you may try to associate it with something that is going to be observed as an outcome. No, empty set means nothing happens, and if you perform an experiment, that event never occurs. Okay. So the empty event, the empty set event, never occurs for certainty. That's why we have a probability of 0 associated with it. Probability of 0 means that the event that contains the event that is the empty set. No, it never happens. Okay, so you can be relaxed in that regard. That this is a probability of 0. We will never observe the empty event. Okay, so I hope it's clear.
Okay, thank you.
So yeah, now let's continue and talk about more examples. So this event and outcome distinction, as I said, was really crucial. So here are some other examples. The set of all possible outcomes. So we described what a sample space is. We described what a single outcome is, specific single observation of a defined experiment, the experiment should be defined very clearly, like tossing the coin 5 times, the result of a football game that ends. So it should be really specifically well defined. That's an experiment. Like tossing a single coin. In that case, the sample space is going to be H or T. It will contain only 2 outcomes when you toss a single coin, if you don't count the case where it came up straight up, which may have some probability, non-zero probability if you think about it. But when you define it something, even when you're tossing a coin, you say that it's going to be in one of those 2 outcomes. And in that case, your sample space is this. And if the sample space is this, again, there will be 4 different events that are here. The 4 different events, all possible 4 subsets. The empty set, the set that contains both of them, the set that contains only head, the set that contains only T. So those are the 4 different possible events you can have in this sample space. If you know the size of the sample space, if the size of the sample space is K, then the number of different events that you can define is 2 to the K, because that's the number of subsets. So for tossing 2 coins, these are the possible outcomes, right? If you toss the 2 coins, first, second, and first, second, if these are the 4 different outcomes. And sometimes we will describe certain events in which the order is not distinguishable. So this is in section 2.3 of the book. Yeah, exactly. So that's a good example. So when we think about Nasrettin Hoca, so I'm reading the chat box comments. So yeah, nothing will happen. That's yeah. If nothing happens, is an empty event. You're right. And here, lifetime of a light bulb. For example, the lifetime of a light bulb, an empty event again. Nothing will happen. Will be probability of empty event. No, that's nothing happens here. I mean, no, that's not correct. Actually, your example, the outcome again. So the outcome, when you define your outcomes, when Nasrettin Hoca trying to chal Amaya in Göl, in the lake. So there are 2 possible outcomes, right? Either something will happen or not. So your outcome space is nothing will happen to the lake or something will happen to the lake. Okay, those are your outcome space. That's not the event that you're defining. The event. Okay, so when you're defining out the outcome space, you should really be careful. Nothing happens and something happens in that case is one of the outcomes. Okay, the empty set really is not nothing happens. The empty set is I don't observe anything. I mean, in that case, in Nasrettin Hoca's case, for example, there is nothing, no such case as nothing will happen, right? I mean, it will mean that you observe something. Either the lake stays still or the lake is going to become yogurt. Okay, these are the 2 possible outcomes that you will observe. The empty set in this case means that you don't observe anything. In that case, it doesn't happen, right? You observe something. Okay, I hope it's clear now. So here, it really, when you say nothing happens is one of your outcomes, you should list it as a specific outcome, and it's not an empty set. Empty set really is not observing anything. I'm not observing anything, and in experiments, it doesn't happen. Okay, it's good. All these different examples, I hope it clarifies the event sample space, because we are going to build upon on these things. This foundation, it will. We will now come to some interesting problems that build upon set theory. I will solve interesting problems in the second hour as well. Okay. But yeah, an event, any collection of possible outcomes, any subset of the sample space. And here are the same examples I gave. If the sample space contains n different possible outcomes, it will yield this many different events. If the sample space is 1, 2, 3, 4, 5, 6, it's going, if tossing a single die, there will be this many different events. What are these events in that case, for example? What is an event here? For example, you toss a die, the outcome is an odd number. That's an event. Okay. In this case, for example, when we talk about we have a fair die, we can sometimes say equally likely outcomes. If all these outcomes are equally likely, then we can assign that probabilities to them, to these single events like that. And that, but first we need to define the probabilities and events, mutually exclusive events. These are really important because when you, for example, when you toss a single die, getting a 1 and getting a 2 are two mutually exclusive events. You cannot, if your event is tossing a single die, you cannot get 1 and 2 at the same time. It has a single face at the top, right? So events that outcomes, or I mean, we will just then outcomes by themselves, individual outcomes here, all these individual outcomes, they are mutually exclusive. And we are going to extend this notion of mutual exclusion to events, all right? For example, let me define two mutually exclusive events, not outcomes. Getting an odd number at the top and getting an even number at the top are two events. When you toss a single die, getting an odd number and getting an even number are two events that are mutually exclusive, which means that they don't share an outcome. These two events, since these are sets, we can talk about set operations like set union and set intersection about them. Set intersection refers to the fact that both events happen at the same time. Then you may, again, if you're confused about outcome and event terminology, you may at this point again argue no two events happen at the same time, right? Which is wrong. Okay, so this statement that I just said, no two events can happen at the same time, is wrong. Let me just give you two events. The event that you will get more than 4 when you toss a die, okay, getting a number more than 4 and getting an odd number. These are two events. Getting an odd number as an event, getting a number which is larger than or equal to, greater than or equal to 4. These two different events, are they mutually exclusive? No. When we get a 5, okay, which is an odd number, and it's greater than 4, it means that both events occurred, okay, both events happen. So intersection of events will mean that this event occurs. So it's possible to have an odd number and a number that is greater than or equal to 4. Okay, so when we define events as sets, when the two events, if they don't share an outcome, which means that if their intersection, these events are really subsets. If their intersection of these events is an empty set, if they don't intersect, it means these events are mutually exclusive. Okay, I'm going to define, again, there are two terms that you should not confuse, mix together are these two things. But I should talk about it later, but let me just give you a heads up. Mutual exclusion and independence. These are definitely not equal. This is very important. Two events being independent, we are going to be using this term, independent events. Independent events and mutual exclusion are completely, totally two different terms that you shouldn't be confused, okay? I haven't defined what independence is yet, but I just defined what mutual exclusion is. If the intersection of these two events is an empty set, if they don't share an outcome, they are called mutually exclusive events. Two mutually exclusive events that I gave was getting an odd number when you toss a single die and getting an even number when you toss a single die. These are two mutually exclusive events. Another thing about events is events may be exhaustive, which means that their union is equal if you the union of those events is equal to the sample space. For example, getting an odd number and getting an even number. If you take the union of those events, which means in English that it's going to be this event or this event. For example, when you toss a single die, you will observe either an odd number at the top or an even number at the top. Yeah, you will say, duh, this is of course the case. All right, so I mean, what the statement that I just made seems nonsense, but it seems nonsense because I just described the entire sample space. Of course, you're going to get an odd number or an even number because when you add those two events up, you get the entire sample space. So it means you're going to get something. In that case, these two events are exhaustive events. Usually, an event also, I just defined some set operations. The intersection of two events means that this event and this event happened at the same time. There, it means that we observed an outcome which is in their intersection set, like two events happening at the same time, getting a number which is larger than 4 and getting a number which is odd. Okay, if the outcome is 5 when you toss a single die, that's the case. Yes. Now, I haven't defined independent events yet. Exactly. Independent events can share some sample space because I haven't defined independence yet. I'm going to come to that. Independence really is not equal to mutual exclusion. It's something else. So here, intersection means both events happen. Union means this event or this event happens. Okay, and there is also another set theory thing is complement. Okay, this event happens or this event doesn't happen. So this or means that it doesn't happen. For example, if E is the event that we get an odd number, its complement will be we don't get an odd number. All right. So these two events, it's the event A itself and its complement, are both mutually exclusive. Okay, you cannot have the same time. You cannot say you get an even number and you don't get an even number at the same time as an outcome, right? Those complements in set theory, it's for example, if this is our sample space, if this is event A, I have here, and this is my sample space, the A complement will denote all the outcomes outside the set A. And as you can see, their union gives the entire sample space. They are mutually exclusive and they are not intersecting. Now, at this point, before we actually, since I have mentioned the term independence, before the break, I will just define what independence is so that you understand it's different from mutual exclusion. And after that, we are going to have a break. Now, this is what independence is. Independence in English means that the occurrence of one event does not change the probability of the occurrence of the other event. This is what independence means. Okay, so in other words, for example, here are two events, A and B. Okay, now I can talk about, when I talk about the probability, associate probability to these events, I will talk about probability of event B, for example, okay? I don't know which outcomes are there. This intersection you see here, A and B occurs, both events occur. This is, as you can see, these are A and B are not mutually exclusive events if there are some outcomes here. And there are some outcomes outside A and B. Let me use a different color to indicate these individual outcomes. So if I have outcomes that are outside, if I have outcomes that happen only in case of event B, and some outcomes are shared by event A and B, and some outcomes are only in event B like this. So these are my outcomes. Now, these two events, since there are some outcomes in between A and B, as you can see, they are not mutually exclusive. They are also not exhaustive. As you can see, there are some events that are outside between A or B, outside A or B. So they are not mutually exclusive. They are not exhaustive, but they can be independent. As I said, let me repeat what independence is. Independence means that if you know event A occurred, this knowledge does not change the probability of event B occurring. All right. Now, what does this mean mathematically? I will show it to you right now. Imagine we have, now I'm going to write here the number of outcomes. If all the outcomes are equally likely, if there are X outcomes here, and if there are Y outcomes here, there are Z outcomes only in this part, and there are W outcomes here on this part. And if these are the counts of outcomes, there are X outcomes in this region that belongs only to A, Y outcomes that only belong to the intersection, Z number of outcomes that are here, and W outcomes here. They're the number of outcomes that I'm writing here. And if all the outcomes are equally likely, the probability of event B is going to be Y plus Z divided by X plus Y plus Z plus W, right? What is this X plus? So the total number of outcomes are X, Y, Z, W. That's the total number of outcomes. And the outcomes that are inside event B are Y plus Z. All right. So this is the probability of B. Okay. Now, what if I told you that event A has occurred? Okay. Event A has occurred means that, so given this knowledge, event A has occurred, just get rid of all the outcomes that are outside X plus Y. So one of these X plus Y events have occurred. What does it mean probability of B did not change? What is the probability of B? If you know event A has occurred, what is the probability that B has occurred too? Any idea? If I tell you event A, you can write in the chat box. If I tell you that event A has occurred, I know that. I don't tell you the specific outcome. I just tell you this information. Event A has occurred. Exactly. Very good. So in that case, if you know event A has occurred, probability of event B is going to occur is going to be equal to Y divided by X plus Y. Because event A has occurred now reduces your entire sample space to event A only. So this X plus Y becomes your sample space in the light of this knowledge event, because I tell you something certain, event A has occurred. Okay, this certainty make your sample space being reduced to X plus Y. And the probability of event B occurring in this new sample space is the number of outcomes that belong to event B is equal to Y. That's Y. Now, in independent events, the thing that is at the top here is equal to this one. So if Y plus Z divided by X plus Y plus Z plus W, if that number, if you compute this number, if it's equal to Y plus X plus Y, what does it mean? No, if these two entities, if this probability and if this probability are both 0.6, for example. Now, if I tell you event A has occurred, and I tell you what is the probability of event B this time, again, it's going to be 0.6. If that's the case, A and B are called independent. Okay? This is what independence is. As you can see, it's totally different from mutual exclusion. Again, in terms of the English language, independent immediately, if you try to imagine what independence is, you immediately imagine two sets that are separate, right? That's wrong. Don't imagine like that. In this course, these two terms, in mutual exclusion and independence, they are different. Independence means, when you think about independence, think about this picture. Two events may be independent and they may intersect. Okay, it means that they're not mutually exclusive. Independence means that knowing of one event has occurred doesn't change our belief, doesn't change the probability of the other event, which mathematically it means that this ratio, the ratio of the entire set of B over the sample space, is equal to the ratio of the intersection part to the entire size of A. So these two ratios are equal to each other. This is what independence means. And independent means that if somebody gives you that information, oh, A has occurred, will you change your belief on whether B is going to occur? No. If you don't change that, it means these two events are independent. All right. So these are really important terms. I hope it's clear. And we are going to talk about that. Let's have a 10-minute break now. It's been an hour. I'm going to stop recording. Let's have a 10-minute break, and I will see you all in 10:50.